Okay, so video 4 for worksheet 4, and I'm going to go through and explain basic things. So I'm going to give you an overarching view of what question 1 is asking. It's asking you to show that a particular integral, and it doesn't really matter what these endpoints are as long as a is smaller than b, so you're integrating over a certain area, and then there's some kind of positive function over here, and in this case it's a dx. They want you to show that this is bounded above and bounded below by some certain value on either side. And the way this is to be done for this exercise is that you simply think, okay, you think about this from A to B, and you look and find the highest value this attains. It's over here. And you say, what is the area under the curve? And so this is an overestimate. So this volume, or this surface, this area goes in this box, whatever this area is. And then what you do is you find the smallest value this function attains. Unfortunately, I made it super, super small, so it would be like down, way down here. So whatever that area is would go into that box over there. So I think I meant to maybe start this function here, in which case I would have drawn the line here, and then that would be the area. Okay, so that's how you do that problem. So you figure that out. Okay, so the concepts you need for question 2 is you have a function, and the important thing about this function is it's concave down. This is an important clue to this problem. So it is sine of x in your problem, but it doesn't actually matter. It matters that the problem involves a concave down function, or strictly concave up would be the opposite effect. But the concavity does not change sign. And so if you were in my class last year, you know that I like to think of concave down as spilling water. It looks like a little cup that spills water. Concave down, and concave up is the opposite. It holds water, and it looks kind of like an upward shape of a cup. This is a concave up shape. So if your entire curve is concave down or concave up, it can help you determine whether you're getting an over or under approximation when you do the same trick we just did in the previous question, and let's say you averaged the high and the low estimate. Okay, so one of the questions you need is average value of a function. So an average value of a function from a to b is going to be the integral. I'm going to give you the generic thing, and you're going to actually calculate specifically for this exercise. But the average value is going to be, you're going to integrate a to b, f of x dx. That's the whole area down here, and then you divide by b minus a. That is the formula for average value. And again, in these exercises, we're often giving you strictly positive area, but the formula is the same whether it's got positive and negative parts to it or strictly positive. It's the same thing. Okay, so the physics will determine whether there's any negative values in your function. So this is the formula you need to use to answer a lot of the questions, subsections in question 2. I'll give you another clue as to how you can approach this question C in question 2C. Okay, so this is going to be more generally applicable as we continue in the semester. This kind of concept should come up again and again. If you have a concave, again, the concave up or down situation, if I'm getting this kind of shape, all right, and I want to do an estimate, I'm going to use some kind of trapezoid. Whatever my trapezoidal answer is going to be too small. Okay, but if, for example, the curve had been concave up in this situation, and I had used a trapezoid to approximate the area, then my trapezoid will be too large. It would give me an overestimate. Okay, and of course the opposite happens for decreasing functions, so just be aware of that. So this function in 2c that you're dealing with is sine of x, so you can split it right down the middle, and you can do two little trapezoids, both of which are going to be, well, you figure it out. I'll let you finish the sentence and figure out why all that logic works. Okay, so that's your clue for question 2, or set of clues. Okay, so for question 3 on the worksheet, you have some kind of squiggly thing, and you have an axis, and you have, it says the graph, this is f prime. And it's often the case when we give students f prime and ask them questions about f, it just messes up their head. So just be aware, first of all, we're giving you f prime and asking questions about f. So I want to practice some of those, and then you will be able to do it yourself. But let me give you some examples. It's easier to think about it going the other way first. Let's say f, and what is f prime when you have f? So typical thing we do is like a parabola. And pretend like it goes down to 0. There we go. It doesn't actually matter. It doesn't matter where that axis is. Okay, but it matters in f prime where the axis is. So what happens is, okay, f prime is 0 when we get a max or min on f, so there's a 0 here. And the derivative is positive over here and negative over here. So in fact, a parabola, when you take the derivative, it does become a line. So if you see a shape that locally looks like a parabola, you should kind of estimate that it looks like a line. So how do you undo this sort of thing? So I'm going to imagine I have f prime and I want to work backwards to f now. And I've put these dotted lines, dotted curvy lines in between what I consider to be the most important part of f prime, which is what happens when it crosses the axis. Now, if you have a situation where you touch down, it's more complicated. But in this exercise, you only have order 1 cut-throughs, so it's not that difficult. The other thing you have to realize is even though just for your own sanity, you're probably going to put an axis, a horizontal axis on your f, it actually is irrelevant. That's the whole idea of constant of integration. But the point is, if you're looking at f prime, and you know that these have to be maxes or mins, well, which ones are maxes and which ones are mins? So let's zoom in on this one right here for fun. And what we know is since the derivative is positive, it must be first an increasing, and then it has to be sort of flat and then decreasing. So this must be reflective of some kind of max. And we have the opposite thing happening over here. Down here we have a negative derivative, and then it's flat, and then it's positive. So we must have a min that occurs in f. This also must be, by the same logic, a min that occurs in f. So what you do is you go back to your original function and you estimate that, and you say, for example, like, okay, 1, 2, 3 maybe. So you say, okay, that's roughly at 3. I need to put a min here. I don't care where. It doesn't have to be on the axis or anything, but I just put it there for fun. Okay, and then 1, 2, 3, 4 maybe. 1, 2, 3, 4. I need to create a max, but it has to be consistent with the other part of this thing over here. And I need a min, let's see, 1, 2, 3 units later, maybe over here. And again, right now I'm not being that perfect. It's good enough. And so it's good enough. And so what you should do on your worksheet is not worry that much about what happens outside of the axis crossings. We will worry about refining that later, but to answer the questions in question 3, it's enough to just really focus on where those maxes and mins occur and just kind of estimate the general shape of what f should look like. Again, this is kind of an art. You develop it over time, but the most important part is to make sure you put the maxes and mins in the right places relative to the x-axis down here. So make sure that if there are roots at f prime, that this is reflected by having the correct either max or min in your F. The other clue, though, you do need to be aware of when doing these problems, that you're going to need it for question 3C. You should think of this. I keep going back to this in my mind and trying to help you think about this. F prime is kind of like your bank deposits and withdraws, okay? And F is your bank balance, okay? So if you have a whole bunch of deposits, this is positive, and just a few withdrawals, that means you have, over this period of time, your bank account is going to be higher. So like, for example, F of A has to be bigger. Whatever F of A is going to be smaller than F of B, because you've earned money from, from A to C, and then you've gotten rid of a little money from C to B, but you have to look at the relative sizes of these humps, and you've lost less than you gained, so overall you're still better off at time t equals B than you are at time t equals A. Again, just think of it in terms of bank deposits and withdrawals as being F prime, and your bank balance is F, and that will help you get your bearings on this question. Okay, so question 4 really focuses on even and oddness. This is a recurring theme in mathematics, and it plays very well with integrals and derivatives. And what it means for a function to be even is that f of x is equal to f of negative x. What it means for a function to be odd is f of x is equal to minus f of minus x. A function can, except for y equals 0, a function cannot be both even and odd. It is actually made up of odd and even components. You can take any function. This is kind of something I didn't know till I was in grad school. You could take any old function you want and split it up into an even function and an odd function. That's pretty cool. Okay, but you don't need to know that. You just need to know that each of these has its own special properties. And when you're looking to do integrals, if you're looking to do an integral from minus a to a, for example, of an even function, you could just do half of that integral. Okay, so you think about an even function, it's just like x squared, or an odd function is like x cubed, and that's a good candidate to have in your mind. But notice that what happens is the integral from 0 to a is going to be the same as the integral from minus a to 0. So that's just something to keep in mind. And then what happens is for the odd integral, you have a similar thing that's actually even nicer in some ways, is if you go from minus a to a, the whole thing wipes out. So the odd function, you have the positive and the negative integral are the same magnitude, and then they're going to wipe each other out. Okay, so that is the key to what happens in question 4, and I'll let you answer the rest of that. Okay, so I told you also at the top of this video, I put a note in there that you should be also watching this video, How Fast is an Arrow, on Michael Robinson's channel. So if you want to go directly there, it's youtube.com/Dr. Michael Robinson, and then you can search for this video, or you can just use the link in the grid to get there. Okay, so the point is we're going to use this method for this question. So this is the part of the video. Actually, you should just watch the whole video because it's one of his really fun videos. I think I'm prejudiced because my kids are in the video. It's both of our kids, obviously. So anyway, the kids in question, Theodore is the little one who is 8 in the video, and then that little red curve. Okay, so this red curve is Theodore's bow. It was an inexpensive bow we got on Amazon that was for young kids. And then this blue bow is one that Zachary made for me, and he was measuring that in the video. So you can see, watch the video and see him actually measuring that. Zachary, at this point in the video, he would have been, is still 12 years old. Okay, so Theodore is 8 and Zachary is 12 in the video. Okay. So you probably don't have to watch the entire video in order to get the question right, but like I said, I think it's a fun video, so I recommend you watch it. And that's all I need to tell you, because that's fully explained in Robinson's video. Hope you have fun, and I will see you soon. Bye-bye now.